Attım.
Stajyeri hikayeleri nasıl gidiyor arkadaşlar? Stajyeri bulamayan var mı? Aramadınız mı? Arıyor musunuz? Bugün mezunlardan birkaç kişi geldi de bu gönüllü yazılım yapıyorlarmış. Bayağı bir adama ihtiyacımız var diyor. Yalnız diyor yaz boyunca çalışacak ve diyor yazdan sonra da diyor aynı proje devam etmesini, çalışmasını falan istiyoruz diyor. Ortem Elektronik, bizim eski mezunlardan Mehmet Kocabaş'la Anıl Apaydın herhalde söyledi, belki tanıyorsunuz. Bugün geldi yakında bir şey gönderecek bana, işte şartlarda şurada falan. Bir de bir iki hocayla da anlaşmaları da var. Yaptığı işi bitirme olarak da yapmam falan durumu da olabilir. Yani sorular staj yaparlar mı falan diye de üçlerden sorular. Ben çoğu bulmuştur diye düşünüyorum ama çoğu bulmamış gibi. Kaç kişinin var stajyeri? Kesin. Ya çok bulanla bulmayanların sayısı aynı gibi. Diğerleri yapmış, yapmayacak herhalde. Tamam, ben onu size yollayayım. Eğer hoşunuza giderse adamlar iyi adamlar, benim sevdiğim öğrencilerdi. Onlar beni çok sevmiyordu ama her zaman olduğu gibi ben seviyordum çok. Çalışkan adamlar iyi iş çıkarıyorlardı. Bir şeyler öğrenirsiniz. Gömülü yazılım yapıyorlar ama Türkiye'de neyse bu gömülü yazılım yeteneklerimiz de kanımızda var bir yerlerde. İyi yapılıyor. Başka yerde pek yapmak istemiyorlar herhalde. Çok fazla iş gücü mü gerektiriyor? Her bir proje ayrı yazılım mı gerektiriyor? Yapıyorlar. Ticari olarak başlarlar. Böyle piyasayı öğrenmeniz falan açısından da çok da büyük bir firmada değil. İşleri de falan görebilirsiniz. Güzel bir fırsat olabilir. Özellikle bitirmeyle falan birleşirirseniz güzel bir bitirme de çıkar. Onlar bana ilanlarını yolladıkları zaman ben derste size onu şey yaparım. İlanını yönlendiririm. Tamam. Buna bir zahmet, sonuncu bu da. So the last time we talked about, okay, for the deadlocks we did three things. First, we detected the deadlocks. Okay, I gave you a few algorithms to detect the deadlock, either a single process or a multiple process. Then we talked about, once we detected the deadlock, what can we do? There is not much you can do about the deadlocks once you detect them, because I mean all the things that you can do, like killing the process or the preemption or the rolling back, either you're losing data or it is very difficult to implement. Okay. The other thing was that after detection the algorithm, we said that let's avoid the deadlocks by keeping ourselves in a safe state. So we talked about, is my state safe algorithms. I gave you a few algorithms on that, including that multiple resources thing and the bunkers algorithm. And then we are talking about now, let's build an operating system that never have a case of a deadlock. Okay, it is not prevention. Okay, it is not detection. It is not avoiding the deadlock. It is completely eliminating the deadlock. We said that for a deadlock to happen, we need these four conditions: mutual exclusion, hold and wait, no preemption, and circular wait. If we eliminate one of them, only one of them, then we wouldn't have any deadlocks. For the mutual exclusion, we talked about spoolers, like the printer spooler. What is mutual exclusion? Only one process can use that resource. If more than one process can use that resource, if many of them can use it, then there is no mutual exclusion. Then we said that instead of somebody using the printer, holding the printer, only one process uses the printer. The rest of the processes hands the jobs over to the other process. This is called spooler. So we would have a printer spooler. We have been using this for a long time, for the last 40 years. That would be one solution for the spooler, but sometimes spoolers are not convenient. For the printer it is okay, but for the scan job or for the tape drive or maybe for the CD-ROM, spoolers may not be appropriate. The second one was the hold and wait. Hold and wait. One process is holding a resource and waiting for some other thing that causes the deadlocks. And our solution was for this one. What was the solution for this one? Never have a hold and wait situation. What was the solution? In order to eliminate any hold and wait conditions, what was the solution?
Pre-allocate resources.
Pre-allocation.
Pre-allocation.
Ask for all the resources at the beginning of the process. So try to get them at the beginning of the process. This way, either you get all the resources or you don't get anything. So you don't wait, you don't say hold and wait. You either wait or you either hold. Okay, you wouldn't have any hold and wait conditions. But then we said that it is not always possible to. It is not always possible to know what kind of resources you are going to need at the beginning of the process execution time. And we talked about no preemption. Just preempt the resources, like the preempting the scanner or preempting the CD-ROM, which may not be possible for all the stuff. And then we have the circular wait. Remember, we had diagrams like this. Okay, this was causing the. This was causing the deadlock. This process is waiting for this one. This process is waiting for this one, and this is holding by this one. Okay, this is the printer. This is process one. This is process two. This is the printer. This is the scanner, and these are in a deadlock. So if we eliminate these kind of a circular wait conditions, then we wouldn't have any deadlocks. And the solution for this one was always ask for the resources in an order. Okay, we should have some kind of an order. Image setter is number one, printer is number two, router is number three, tape drive is number four, and CD-ROM drive is number five. When you need a resource, let's say you need printer and a tape drive, you should get the printer first, tape drive later. Okay? You always follow the same order. If all the processes follow the same order all the time, they will not have this hold and wait condition at all, because everybody is following the same order. Of course, the negative side for this one is I cannot assign numbers for all the resources. Some of the resources are very complicated, like the database record resources. I cannot give them some kind of an order all the time. Inherently, there are some circularity between those resources, so it may not be possible to have this one either. So each of them can be addressed to some extent, not completely, but each of them I cannot say that for all the systems I can do this and this and this, because some of them have very serious performance problems, some complexity problems, some of them are not possible. So three things we looked at it. I mean, deadlock detection has problems. Deadlock avoidance has problems. Prevention has some problems. That means that we are not going to solve this deadlock problem altogether. We have to learn how to live with the deadlocks. Okay. Related to the deadlock, there is a live lock. Okay. It is not in the deadlock. Somebody is waiting for somebody. They are holding and waiting, and nobody can do their job, and they are dead. They are not doing anything. In the live lock, there is a lock situation again. The processes are living. Okay, they are not dead. They are waiting for something, but at the same time, what they are waiting for is themselves actually. Let's look at these two processes. Okay, again, they have the same resource one, resource two, and one. They are using the inverse order, so there is a kind of a deadlock situation here, but we are calling this live lock. In case they would go into a deadlock, they change their policy. They acquire the lock for the source one, then they try to acquire the lock for the source two. If they don't get the lock, if it has failed, then they release the resource one, wait for some fixed time, then they try to acquire the resource number one. Why are they doing this? Because they are doing this because when they cannot get the resource number two, that means that it might go into a deadlock, right? Because this process might have the resource two, and this This has the resource 2. This is trying to get the resource 1. This is trying to get resource 2. If I don't have these conditions here, if I don't check for these conditions here, then I might have a deadlock, which is bad. That's why when they cannot get the second resource or the first resource in this case, they release the first resource, wait for some time, okay, then try to acquire the resource number 1. This way they are trying to prevent any deadlock algorithm. But this is causing another problem. The problem is, since they are waiting for the same amount of time, they get let's say this is running on CPU number 1, okay, this is running on CPU number 2. They get the first resource and the second resource at the same time, trying to get the second and first one at the same time. They will both fail. They will release their resources. They will wait for a fixed time. They will get the resource 1 and resource 2, and they will go back to while loop, and they will not get the resource 1 and resource 2 again. So they will continue this loop indefinitely. They are living, okay, they are not in a deadlock, but still they cannot continue and do their jobs here. Okay, they cannot do and continue and do their jobs there. So this is called live lock, not deadlock, but the live lock. So this is a known problem. You might say that instead of waiting for fixed time, you would wait for what? Wait for some random time, right? Not fixed time, random time. If you wait for some random time, maybe they will go out of sync. But there is still a possibility for both of them trying to do the same thing over and over again. Couldn't get the lock, and they will release the lock and try to get the lock again. This is called live lock, an alternative, another form of processes locked, being locked, different from the deadlocks. Okay, so this is the deadlock situation. Related to deadlocks, okay, this is not deadlock, but related to deadlocks. Another one is starvation. Okay, starvation is not a deadlock situation, but this effect is the same as the deadlocks actually. So let's see how that goes. Let's say you have a printer. Okay, you have a printer daemon. The printer daemon is printing the job that it is assigned to. So the print policy is, the prior to policy is this: always print the shortest jobs first. Okay, if I have a 2-page document and there is another 100-page document, the printer process says that I'm going to print the 2-page document. Okay, so if the system is busy, it is always getting print tasks. Okay, very large number of small page number documents, like the 1-page document, 2-page document, 3-page documents. So the printer will keep printing those small jobs. The 100-page document will never get any chance to be printed. Okay, so it will wait and wait and wait. So that's called starvation. It is not in a deadlock situation. The printer is running. Somebody is using the resource, but one of the processes are not being handled because it is trying to print a very large document, and our policy is always print the small document first. So this is called starvation. There are processes available, there are resources available, processes are using those resources, but some of the processes are being held because they are in a starvation situation. This is not a deadlock again, but the effect is like a deadlock. One process is never getting anything done. Okay, so this is related to again to deadlocks. Deadlocks and live locks. Okay, for most operating system, we just ignore them. Okay, we just pretend like those switch algorithm. We don't pretend it will never happen. Because the solution for these is you will have to write specialized code to prevent these live locks and the deadlocks or the starvation code. Okay, if the problem is too much, if I am getting a deadlock 2 or 3 times a day on an operating system, then that problem is a serious problem. It has to be handled. But these deadlocks and live locks do not happen very often. very often because most of the resources are actually for the operating system is preemptible, like the memory or the CPU or the network card or the other stuff. Okay, they are preemptible. Since they are preemptible, one of those conditions are not met, so I will not have deadlock most of the time. If I have the deadlock, then I will just ignore it. I will not do anything. So what's going to happen? What is going to happen to my process is they will hang there. They will not finish their jobs. So the user will realize it, and user will kill those processes, restart the processes again, or restart the whole operating system. And this is the most of the time the solution for the deadlocks or the livelocks or the starvation problems. Okay, so this is the end of the chapter number 6 on deadlocks. If there are no questions, then I will start a new chapter. And yes.
Starvation çözüm olarak bir şeyi baştan başlatmak çözüm olmaz ki. Starvation sonuçta proses schedule'la ilgili bir şey değil mi? Büyük olanı vermiyor özellikle.
For the starvation. For this case, if you restart all of your processes again, okay, and if that long page number process bylock is printing the first time, then it will get printed.
Aynı zamanda tek onun olması lazım ki yazılabilirsin.
Well, I mean, maybe there are 10 processes, okay? That large page number process sends this job first, so it will be the first one. So the printer will start printing it because there is no job available at the beginning. Okay. Yeah, well, sometimes, yes, I mean, sometimes it is called operating system bug. Whatever I do, sometimes I send a job to the printer, it doesn't print it at all, right? Bazen öyle değil mi? Printer'ı gönderiyorsunuz, yarım saat sonra hiçbir şey çıkmıyor. Yani ya işletim sisteminde hata var, ya gönderdiğin işte bir hata var, ya printer'da bir hata var. Bunlar ne diyor? İşletim sistemi hataları bunlar ya da programların hataları. Ne yapıyorsunuz o durumda? Ne yapıyorsunuz? Bir printer'a job gönderdiniz, basılmıyor. Bir daha gönderdiniz, bir daha basın. Ne yapıyorsun? O da yine çalışmadı. Ne yapıyorsunuz? Benim yaptığım şeyi, gönderdiğim şeyi PDF dokümanı, PostScript dokümanı alıp birazcık değiştirip, tamam mı? Bir daha göndermeye çalışıyorum. Ya da 2 parça göndermeye çalışıyorum. Yani bunlar hiçbir şey değil. Şimdi ne olacak? Yani bizim bilgisayar gibi crash olacak halimiz yok. İnsan çözüm bulmasını seviyor. Problem şu, eğer günde 3'te, 5 defa, 100 defa, 20 defa sistemi restart etmek zorunda kalıyorsam kötü. Haftada bir, ayda bir bazı proseslerin, bazı print job'ların benim basılmıyor. Onu idare ediyorum. Bir şey yapmak da istemiyorum. Çünkü onunla ilgili bir çözüm arasam internette, arasam, bulsam alırım, bulurum. De değmiyor yani. Ayda bir ona 3 dakika fazla zaman harcamak yerine bir günün 3 saatini o problemi fix etmek için çözmek fazla geliyor. İşletim sistemlerinde de öyle. Yani adam 70 milyon satır kod yazmış, hala içerisinde bug dolu. Yani deadlock'a zaman harcamak yerine 10 milyon daha satır koyup, onun yerine elindeki 70 milyon satırın günde 2 defa Windows'u crash ettiren taraflarını fix edersen daha akıllı bir yatırım olur diyor. Mühendislik dünyası bu şey değil, matematik dünyası değil. Matematikçiler bu işi çözelim diye çok uğraşmışlar. Mühendisler diyor çözmene gerek yok zaten çok fazla şeyi almıyor. Yani baştan beri işletim sistemlerini söyledikleri bu. Tamam, başka soru yoksa security chapter'ına başlayalım. Çok fazla ilerleyemeyeceğim security chapter'ında. Şöyle temelleri hakkında birazcık konuşalım. Birazcık encryption falan hakkında konuşalım. Password'ler hakkında konuşalım. Onlar. Okay, so the security first. This is what I'm going to do a little bit. Not all of them, but just some of them. We will talk about the system security, what is operating system security, and how the operating system contribute to system security. If we trying to develop a secure system, what do we need to do? What kind of demands? What do we demand from the operating system? And I will make a simple introduction on this important topic. So, informally, security is this. Security is keeping unauthorized entities from doing things you don't want them to do. Okay, these entities could be other users, external users, non-users of the system, or some other programs, system programs application programs or the programs living on outside of the operating system. Either if they are not allowed to do something, okay, some people or the processes or the programs, whatever, security is we keep them doing that thing that is prohibited thing. More formally, security is divided into these categories: confidentiality, integrity, and availability. Okay, we will talk about them in more detail in a few minutes. Sometimes people use these terms interchangeably, security and protection. Okay, security and protection sometimes mean the same thing, but the book says that, okay, they are slightly different. Security refers to the overall problem, overall security problem. Okay, the term security. The term protection mechanism refers to the specific operating system mechanism used to safeguard the information in the computer. So remember what we are trying to prevent other entities doing things that we don't want them to do. So if I have specific mechanisms for, let's say, for unauthorized people to access something, I have a protection mechanism for that one. For unauthorized processes to do something, if I want to prevent it, then I have another protection mechanism for that kind of a task. So security and protection usually mean different things, but most people use the same term to refer to security. So let's look at these three terms: confidentiality, integrity, and availability. Three components of security. Okay. For a secure system, there are three goals. Okay. Data needs to be confidential. Okay. Only people who are allowed to see that data, or only the processes that are allowed to see the data should see them. There should be a data integrity and system availability.